So the purpose of this presentation is to present a decision support tool that we developed. So a tool that can be used for process monitoring and for real-time energy inefficiencies detection and diagnosis. So for this presentation, I will talk a bit about the methodology that has been used to develop this tool, but the focus will be more on the case studies. And of course, I will share with you at the end the lessons learned. So as you may know, operators in pulp and paper mills are facing daily issues related to abnormal situations, such as a decrease in the process performance or a deterioration in the product quality. And these abnormal situations can affect the energy efficiency of the process and can also affect the profitability of the mill if they are not resolved quickly. But until now, the detection and diagnosis of abnormal situations rely only on the human expertise. However, to find the root causes of abnormal situations in complex processes can be challenging and time-consuming even for experienced process engineers or process experts. So for this reason, we think that mill operators or production engineers need decision support tool to help them to deal and to better manage the abnormal situations. So therefore, our project aims to develop a decision support tool that can help operators to detect and to diagnose energy inefficiencies and propose them corrective actions. So to be more specific, the role of the tool is to detect any situation of where there is a significant decrease in the energy efficiency and reduce the exploration time which is needed to find the root cause of this inefficiency. So to develop this tool, our approach is to take advantage from the powerful of machine learning techniques to learn and to extract knowledge from the data. And of course, we cannot rely only on the machine learning, but our approach is also to combine the machine learning with the process expertise in a certain way to create a kind of synergy in order to develop accurate and practical decision support tool. So this diagram shows the methodology that has been used to develop this tool. So I will not go in details, but what I will what I want to mention here is that the methodology combines many unsupervised methods and many supervised learning methods or classification methods, and it tries to take advantage from each method in a certain way to increase the robustness and the accuracy of the tool. So the classification algorithm can detect or can predict a cause of an energy efficient, known cause of energy inefficiency, whereas the unsupervised method can detect and isolate a novel cause by showing what are the contributing variables to this inefficiency. And of course, all the models are developed with using the historical operating data. So now I will talk about the case studies. So the first one is the monitoring of the operation performance of a heat recovery network in the thermomechanical pulp mill. So this diagram shows the heat recovery system. So it shows also a part of the steam network. So the system consists of two subsystems: the boiler subsystem, which receives dirty steam from pressurized refiners and produce clean steam. And the second subsystem, it's a combination of direct contact condensers and direct contact heat exchangers, and receive the dirty steam from atmospheric refiners and recover the heat to produce hot water for the paper machines. So there are two situations related to the energy inefficiencies of this system. The first one is the opening of the dirty steam heater vent valve. So we have an energy loss to the atmosphere. And the second one is the opening of the fresh steam valve to the heater. So in this case, we have an increased exhaust from the turbine, and then the power production will be decreased. So to find the root causes of these two situations, we applied the methodology that we developed. So what we did, we took the historical data for each subsystem. So here it's shown a sample of reboiler data. Then we use the clustering methods to cluster the data, and we identified what are the clusters representing abnormal operation, meaning that the vent valve is open. Then we used data analytics and pattern analysis techniques to do the interpretation of each cluster. So then we were able to associate a cause for each cluster. So by doing this, we were able to do the labeling of the data, and we use this labeled data to train the classification model in a way that it can predict the cause when it will be installed online. At the same time, we took the normal operation data and we developed a multivariate statistical model. And the role of this multivariate statistical model is to detect and isolate a novel cause of the inefficiency. So it can show what are the contributing variables to the inefficiency. So one, for the online operation monitoring. So the two, here I show the example of the boiler system. So when there is an opening of the vent valve, the classification algorithm and the unsupervised model will receive the online data. And when there is an opening of the valve, so the classification model can show what is the possible cause and also what are the proposed actions. And the unsupervised model will show what are the contributing variables to this situation. So then the decision maker, meaning the operator, can compare between the two outputs and can decide what is the action to take. So for the second case study, it's the monitoring of the energy performance of a paper machine. So for this, for the paper machine energy monitoring, we can use different KPIs. Example, we can use the last press consistency for the wet end, meaning the forming and the press section. We can use the evaporated water to consume steam ratio for the dry end. So in our case, we use the specific steam consumption of steam per ton of produced paper. And of course, this covers.
Sorry.
Oh. So in our case, we use the specific steam consumption, meaning the ton of steam by ton of paper. And as I said, this covers the two parts of the paper machine, the wet end and the dry end. And we use the methodology. So we took the historical data. We defined what the normal operation and the abnormal operation, meaning that we defined many peaks of overconsumption of steam in the paper machine. Then we used data analytics techniques. In our case, we used the Explorer software developed at Chemical Energy to analyze each peak of representing the overconsumption of steam in the dryer. So by doing this, we were able to associate to each peak. We can see what is the root cause of this peak. And by doing this, we were able to label the data and use the labeled data to train the classification model. So the same thing as in the previous case study, we use the normal operating data to develop a multivariate statistical model. So here I show examples of the identified causes. So there are many possible causes of the situation of overconsumption of steam in the paper machine. Some example is the freeness decrease of the pulp, or significant drop in the vacuum levels. So as you can see, there is a lot of possible causes. So if we rely on, it can be very challenging to identify the root cause of situation of energy efficiency in the paper machine if we rely only on the process expertise. So for this case study, we implement the tool in the mill. Here I show a screenshot of the tool. So as you can see, there are two outputs. The first one, it's the possible cause of an inefficiency, meaning that situation of overconsumption of steam in the paper machine, and also what are the contributing variables to this situation. So before to transfer this tool to the mill, we did tests for many weeks to verify and validate the accuracy of the tool. So in our case, we had remote access to a workstation in the mill where the tool is installed. So this makes possible the testing by ourselves. So during the testing phase, we noticed an accuracy of about 98%. And of course, the tool was installed in advisory mode, and there is no meaning that there is no interference between the tool and the control system. Another case study where the tool is applied is for a black liquor concentration system. So for this, we have 3 KPIs. The first one is the heavy black liquor solid concentration, the steam economy of the entire system, and the combined condensate conductivity. So these 3 KPIs are related to the energy efficiency of the craft process. And the last case study is the black liquor recovery boiler energy and environmental performance monitoring. So in this case, we have considered 2 KPIs for energy efficiency: it's the produced steam to black liquor dry solids ratio, and for the environmental performance, it's the TRS emissions. In terms of potential impacts, so the impacts are case specific. So for the stated systems, for the case studies that we made, we estimated potential steam saving of about 2.5 tons per hour for the boiler system, 1.6 for the evaporators, 4.8 for the recovery boiler, and 1.2 tons per hour for the paper machine. So the savings are around $200,000 for the paper machine and around $800 for the recovery boiler. But besides the energy savings, we have other benefits. For example, the increased capacity of the studied systems and the reduction of the environmental impacts for the case of the reboiler. For the lesson learned, so I can say that even though this tool was applied for pulp and paper processes, for energy inefficiency detection and diagnosis, but we think that the approach is generic and flexible, so it can be adapted and used for a wide range of industrial processes, and can also be used in different contexts. For example, to diagnose the abnormal events leading to process yield decrease or product quality deterioration, or for any environmental issue. For the development phase, one of the lessons learned is that combining domain knowledge and machine learning is a promising approach. It allows to develop a tool that can be implemented, meaning practical decision support system. Also, beside the availability of the data, we think that the involvement of the mill staff in the development phase is important. For the tool deployment, we think also that what we learned is the testing phase is important to validate the accuracy and the robustness of the tool, and also to demonstrate the the value of the tool. The fact that there is no interference between the tool and the control systems helped to the acceptance of the tool and its implementation in the mill. For the tool use, so even though the tool showed a high accuracy for detection and diagnosis of abnormal situation and energy inefficiencies, but this accuracy can be affected by so with the time can decrease with time, and we think that it should be the model should be updated if there is major modification in the process or a major change in the operating strategies. So thank you for your attention.